I'm going to take a two-dimensional region in the XY plane and rotate it around the x-axis and create a three-dimensional object that has a volume. And I'm going to find that volume using the disk/washer method. My region is bounded by three lines or three curves: y equals 2x, y equals 10, and x equals 0 in this example. So I'm going to sketch that just so I can get an idea of what's happening here. Y equals 2x goes through the origin, has a slope of 2. Y equals 10 is a horizontal line. And then x equals 0 is the y-axis. So I'm looking at this region right here. I can find this intersection point by setting y equals 10 equal to y equals 2x. So that's x equals 5. And I'm wanting to rotate this around the x-axis. So when I do that, it creates this three-dimensional object. And this object looks like if you took like a cylinder and then you hollowed out the center. So you made like a hollow cone in the center of this cylinder. I need to find a way to find this volume even with this hollowed out piece. So what I'm going to do is use this disk/washer method where you slice up this object into vertical pieces and calculate the volume of each of those pieces and then add those together. Take the limit as the width of the pieces goes to 0, and that turns into an integral. So if I take a slice, it's going to look something like this. I'll sketch it here. It's a little hard to see here, so I'm going to sketch it off of that graph as well. There's a piece in here in the center that makes it hollow, so that's why this is called the washer method sometimes, rather than just the disk method. So if I bring this slice out, it looks something like this. It's got this hollowed out piece. So I can find the volume of this thing by just finding the area of the face, the area of the base, multiplying that by the height. I'm going to call the height delta x because I'm going to let that shrink down to 0 in the limit so that I can get an integral. That means that before I get the integral, my approximations for the volume are adding up the area of this outside times the width. So the area of the outside is like a pi r squared for the big circle minus the area of the little circle, so minus pi times little r squared. That's the shaded in red area times the width. When you take the limit of this, as delta x goes to 0, it turns into an integral. I'll factor that pi out. And then what I have left is r squared, big R squared minus little r squared. And then the delta x becomes dx in the integral. The big radius is the distance from this center all the way up to the top point. And no matter what my slice is that I'm looking at, that distance is always going from here up to 10, so it's 10. So r squared, big R squared is 100. And then little r just goes from the center up to this point. And this little one is determined by the line y equals 2x, the slanted line. So if I choose if I choose slices that are further out to the right, then that inside radius is bigger. If I choose them closer to the left, it's smaller. Whatever x value I pick in here, I just plug that into the line y equals 2x. That gives me the exact radius. So the thing that I'm squaring, this little r, is just 2x. Now I'm almost ready to go. I just need to get the bounds. I need to let these x values range from 0 out to 5. So now I'm ready to find the antiderivative and finish up this integral. I'll bring the pi outside, out in front, since it's multiplied times the rest of the function. The antiderivative of a constant is that constant times x. And then this term is really a minus 4x squared. So when I find the antiderivative, it's minus 4/3 x cubed. Going from 0 to 5. So I'll plug in 5 first, and then do minus, and then plug in 0. Notice when I plug in 0, both of these terms will go to 0. So plugging in 5 gives me 500 minus 5 cubed is 125. 125 times 4 is 500. And then there's a minus 0 after that I'm not going to write. So 500 is the same as 3 times 500 over 3. So in thirds, there are different ways to think about this, but basically this becomes a 1500 minus 500 is 1000. So there's my final answer for that volume.